Hello, my name is Thorsten Stremlau. I am the Marketing Work Group Co-Chair of the Trusted Computing Group, and welcome to this session on how to protect the integrity of electronic components and storage devices from supply chain attacks. For the next 20 minutes, I will share standards and regulatory work that's being done to help ensure that electronic components and storage devices are protected from hacking attacks at all levels. When we take a look at all of these different types of things, one of the things that's very important is to obviously cover the legal notice. So this is the legal notice as provided by the Storage Security Summit. But when we take a look at the overall, I guess, landscape, we'll see that most organizations really now really only consider the visible state of their computing devices. They're not really looking yet too much at the provenance and integrity of the device itself and of the components. But provenance is becoming more and more important throughout the entire life cycle of the device. We're seeing a 78% year-on-year increase in supply chain attacks. Very, very much focused right now on software and hardware attacks in that area. 46% of global businesses have encountered at least one supply chain scare in this space since shifting to a remote working model in the first quarter of 2022. And Gartner, you can see here, this is a very enlightening study that they did, really sees that 60% of organizations will be building or procuring critical infrastructure components and mandating supply chain trust principles into their engineering practice by 2025. So it's really, really dramatically up since since 2022, where there's only really been 20% of the same. Now, where is the threat? And this is a really, really old model. I think this is covered in the press a few years ago, and the scare here was, can somebody introduce this little microscopic component that's highlighted by the white circle onto a board, onto a component, or can somebody modify the firmware of a device in transit? Now, looking at it, in all sorts of different areas, this particular hack that I'm highlighting here really was never proven. However, if you do go down to this YouTube link that you can see right here, you'll see some of the examples where this organization that published this YouTube link really goes into depth about some of the possibilities behind this particular hack and how it could be pulled off. And these supply chain risks, as you can see here, really can happen all sorts of different areas, right? Whether it's a component supplier that then they deliver into a subsystem supplier, that subsystem supplier then delivers into the OEM, and at each of these different types of stages, there is complexity and there's additional chains in the supply chain. Once the OEM then assembles the components and puts it into the channel, again, another transit. And lastly, from the channel to the customer. So at each of these different types of steps, there's a traditional and very, very significant risk of a supply chain attack on the device and also on the storage component. And this is something that is actually worrying customers, especially in the enterprise everywhere. Now, a lot of work is being done in the industry in order to protect and to organize against this. So NIST is really a North American organization, but what we see is that their reach is global, right? Many other regions also adopt and look to the NIST standards in order to see where they can go and to align with them in terms of best practices. One of the significant ones here is the NIST SP1800-161 and revision 1. This covers, it's a really, really in-depth document that covers the cybersecurity supply chain risk management practices for systems and organizations. There's a whole bunch of sections in there about how you should assess the risk and deal with risk in the supply chain. And it's actually just been revised in order to include firmware attacks and supply chain attacks like the ones that I'm going to cover. A preliminary draft from the NIST is the NIST SP1800-34, which is all about validating the integrity of the computing device. And it really goes into detail about a best practice on how that should be done. The NIST SP1800-193, and I'm going to go into this in just a little bit more detail in just a second, now talks about platform firmware resiliency guidelines. So how do you now protect the platform firmware on the device and make it more resilient? A while ago, the Biden administration here in the United States issued an executive order on improving the nation's cybersecurity, also called SBOM, Software Bill of Materials. Well, what the security industry and what security organizations have now done is really taken that even a step further, and I'll talk to you a little bit about that when looking at how to now secure, for example, firmware with an SBOM. And so how do we document firmware components using the same principles of a software bill of materials? Now, to my own organization, the Trusted Computing Group, we also have many different standards and work groups. We've actually just formed a TCG supply chain security work group that is working on assembling all of these different types of technologies and standards and publishing white papers and best practices within this space. But two of the many different types of standards and publications that the TCG's put out is, number one is FIM, Firmware Integrity Measurement, and then TCG RIM, which is the Reference Integrity Manifest Information Model. These are very important, and I'll be covering those in just a second as well as we go through. Now, I've been focused, especially up at the top, a lot around North American regulatory and standards work. But as I said before, we can see that this is actually coming down into many other areas, including the EU RED directive, in this particular model. Now, taking a look at all these different models, then this SP1800-161 really talks about, and it's really, as I said, really comprehensive document that talks about the enterprise's visibility, understanding, and control of its supply chain. And what you can see here is that the further away from the acquiring enterprise the supply chain goes, right? So here, for example, we have the supplier that has the direct link to the enterprise, but once we get down to the external system services provider or supplier to the supplier, and now if we go to the supplier of the supplier of the supplier, or even deeper, there's a complete reduced visibility and understanding and control of the upstream supply chain. And again, this is very important from a NIST SP1800-161 is being able to understand whatever level of complexity there is in the supply chain to make sure that you can mitigate your risk. The NIST SP1800-34 now talks about how these things can then be documented, right? So it talks about component, subcomponent manufacturers that produce components or subsystems, and then basically generate a verifiable artifact, right? So this is basically a very detailed documentation, which I'll get into. And my suggestion here is to use the TCG FIM specification. And then, by the way, you can see here that the OEM or the value-added resource reseller that now manufactures the system can now go in and bind each of these verifiable artifacts that make up the system, which is made up of all the subcomponents and subsystems, into an associated verifiable artifact. And then the enterprise customer will then be able to do verification testing, and by the way, then maintain and verify an enterprise IT management system that would then build up on top of this NIST SP 1800-34 Notion architecture. So again, please remember this verifiable artifact. This is something that's very important, and please do read into more detail on this as you go through, because this really defines exactly a really nice process flow of how to verify the integrity of computing devices in that environment. Now, NIST SP1800-193, this is really all about protecting, detecting, and recovering from a firmware or some other type of attack on the device itself. The standard or the publication very, very clearly identifies storage both as the controller, but then also as the storage device itself as a critical boot device and as a critical operating device, right? Obviously. And so again, one of the things that's really important here is what level of access can a hacker have in order to inject or change code on the system in order to do something malicious, right? And if we remember, for example, the SolarWinds attack, that was a fairly minor change in terms of the source code that had severe effects with thousands of organizations all around the world, right? And that was, by injecting some malicious code into the supply chain. This was something that was able to be done. Now, imagine if a hacker is able to inject some sort of a malicious firmware into the device. Let's say if a particular sequence is written to the hard disk drive or to the storage device, that it would now erase itself, right? Imagine the denial of service attacks that could be started in that particular case, right? So there's many, many different types of areas here. If you really want to learn more about how how the NIST SP1800-193 can be implemented, please do read through it. However, I also want to highlight the fact that many are also looking to storage devices as a storage area for critical firmware of all of these other firmware components that you can see up here, right? There's the EC firmware, there's TPM firmware, there's the NIC GPU, power supply firmware, all of these other different types of firmware components. And many of these firmware components, for example, simply don't have the space nor the intelligence to store a backup copy of their verifiable firmware. And so it's becoming more and more important, for example, to lean on storage also as a recovery medium for firmware components in this space. So if you're looking at any of these areas as well, please do have a read through the 193 specification or publication in that particular case, because it really highlights what can be done within this space. Moving on, and please, do go to this blog, as you can see here. It's a really, really in-depth blog that covers, as I said, the software bill of materials, but now taking a look at it from a firmware component, right? So obviously, storage has firmware. Both the controller and also obviously the storage device itself. And today, let's say Carol's compression engine is included in Bob's browser, and Bingo Buffer is included in the Acme application, which includes Bob's browser and Carol's compression engine, right? These could now be things that are there. Now, let's say the industry identifies a vulnerability, let's say with an open source part of the code, which is Carol's compression engine, right? By having a software bill of materials, I can now very, very quickly be able to identify, yes, my Acme application contains Carol's compression engine, and therefore maybe I need to do a revision, maybe I need to patch it. And that's the purpose of the software bill of materials. Expanding this into firmware, we can now see many other different areas in this space. And you can see here, as I said, many of these publications and many of these thoughts are actually quite recent. So please do have a look at this web page as well. It really talks about the importance of documenting very, very clearly, not just software bill of materials, right? That would be software that runs on it, but also firmware software bill of materials, so that down the line, the customers, the enterprise customers, but also government organizations, et cetera, can very, very quickly establish whether a component has that vulnerability or not. And by the way that we can also do this is, for example, by using the TCG firmware integrity measurement, right? Which is one of the specifications that I talked about, right? So in this particular model, what we have is we have a root of trust measurement. And so once the device is powered on, what now happens is that we basically will initialize the PCR platform configuration register back to 0. What now happens is that an event 1 happens, right? So something happens on the device, let's say, and now the root of trust measurement would now look at that event and compare or take that integrity manifest or integrity measurement of that platform and now extend the PCR, the platform configuration register, with the hash of that integrity measurement. And the integrity measurement with a corresponding event now gets logged into memory, storage, et cetera, so that I now have that corresponding event with the record 1 on this particular bit. So again, looking at the firmware integrity measurement down the road, now an event 2 happens. And so what now happens is, obviously, we have a new integrity measurement. It extends the existing PCR value. So we take the previous PCR value and we extend it with the new PCR value of the new integrity measurement. And we store the corresponding event log in memory again, and so on and so forth. And so at any given moment, what we can do is that we can actually see if this chain of events happens in the same way, or if somebody has now modified the code in some sort of way in order to bypass these events. This is why the firmware integrity measurement a publication is fairly important. Please do have a read through it to see into that in more detail. Now, the reference integrity manifest model then defines how you document all of your different components, right? So I mentioned all the way in the beginning when I talked about the NIST 1800-34 is that verifiable information. And so whether you have a direct RIM, reference integrity manifest model, right? And this direct RIM could simply be your RIM attributes, and in this RIM data model basically defines how this data is contained. So you can see here each of these RIMs contain RIM attributes with a payload, and this payload then has information in it, but can then have the contents of a file or some other resource, right? So for example, you could be publishing all of the modules of your firmware in here. You could be publishing, for example, the source of the memory that is in your storage device, or whatever other kind of things are in there. So this is it's actually fairly flexible. And then obviously all of this is then verified by a signature. In the indirect model, let's say you are assembling certain components. Obviously what you can now do is you can take in different types of support RIMs, right? So you could take in other direct RIMs from others, and then assemble those into one. And now basically you create a base RIM that is made up of multiple support RIMs in each of the space. So that would typically, for example, could be an OEM that assembles a support RIM from the CPU manufacturer, from the memory manufacturer, and from the storage manufacturer into one new base RIM. And that base RIM makes up the entire configuration of the machine. Now, how does all this fit together? As I showed you in the beginning, we can now look at the state of all of the integrity measurements, as I said, for using the FIM. And now basically we compare all of these firmware integrity measurements with a RIM source, the reference integrity manifest source, to make sure that nothing was actually modified and that everything is really in its place. Now, in summary, I've covered many different types of standards and regulatory and publications and all sorts of other different types of things like it, right? So my suggestion here is really for components and subsystem providers, they produce the components and subsystems, and they basically create this verifiable manifest or verifiable information. The manufacturer, right, the OEM would now be able to, for the producer of the platform, can then assign or collect all of these different types of things, and with that prove provenance, and then create a new base RIM model within the RIM collection. And by the way, in this particular bit, whether it's the channel partner, a distributor, a partner, or a config center, can now do, or by the way, the customer, they can now do the verification testing on each of these components. And with this, we should be able to meet all of the requirements that you can see in terms of being able to document and protect against supply chain attacks by having very transparent and thorough documentation of all of the components and the subcomponents in devices throughout the supply chain. So thank you very, very much. And with that, I'd like to open it up for questions.